Okay, off we go. So here's where we were last time. We were talking about, kind of started talking into section 2.6, but I hadn't really quite got around to making a point yet. Right? So I've flashed back to some old observations about partial derivatives. So let's see here. So partial derivatives. I'm not going to go through all these details again. We talked about it last time, but slope of the graph. Right? It's a multiplicative factor. It's something that you can write with this expression down here. Now, we've never explicitly done this before, but again, this is a nice little exercise, something to think about. I mean, basically, what's inside the argument of the function here is a fancy way of saying most of the coordinates are going to stay constant because EI has got a bunch of zeros in it, and only one of the variables is going to change. And then another little easy calculation, you could just literally compute this dot product and it works immediately. Okay, so what we have is, four different points of view or whatever you might want to call it about partial derivatives. Okay, so what if I wanted to do a partial derivative, but rather than doing the partial derivative, okay, I'm going to say this in a weird way, deliberately weird. Partial derivatives are in the direction of a unit vector, namely a standard basis vector. What if I wanted to do that, but in the direction of a different unit vector that's not a standard basis vector? I don't even know what that means, right? I mean, the whole idea of partial derivatives is you look at it from the point of view of variables, coordinates, right? It's a coordinate point of view thing. And I'd like to make the case that coordinates are actually a pretty unnatural way of thinking about point in multiple dimensions. There's something very arbitrary about coordinates. And I've prepared a little picture here to illustrate my point. Here I've got these various wavy lines. By the way, this is the same picture twice, pretty much the same picture twice. The background, anyway, is the same exact picture. And maybe these are, level sets of, altitude. Maybe this is a contour map of some hill I'm climbing around on, whatever. Let's look on the left over here. We have our axes set up, and we have a couple of vectors, u and v. And I'm going to make what I think is a pretty clear statement that v is a standard basis vector, right? It's E2. Well, of course it is. U is not a standard basis vector, but that's silly nonsense. Of course it isn't. Look at it. It's not even along one of the axes. Well, it's just not even close. It couldn't be a standard basis vector. All right, here's the thing, though. Why did I set up my axes like this? Right? What is it that dictates that I have to set up my axes this way? Now, you might say, well, straight up and down and horizontal, stuff like that. But if you're out hiking around, which direction is, canonically the correct direction? What is left, right? It depends on where you're standing and which direction you're looking and stuff like that. There's nothing really particularly canonical about that. It's an arbitrary choice, right? So just to emphasize, let's look at what I've got over here. Same basic picture, same U, same V. But now I've set up my axes this way. And now use a standard basis vector. Same vector U. So what does it mean to say that a partial derivative is, well, we're going to hold certain coordinates constant or certain input variables we're going to hold constant? All it means is that you've made this arbitrary choice about how to set up your axes, and you're defining something on the basis of that arbitrary choice, right? It's not anything intrinsic about what's actually going on. We were making this silly observation, couldn't possibly be a standard basis vector, except, you know what? You change your axes, and all of a sudden it is. It is a standard basis vector with respect to these axes. Okay. So what is and what is not a standard basis vector is all dependent on this arbitrary choice. And with that in mind, I'm going to come back down to here and revisit this question of partial derivatives, and partial derivatives are something that nice that happens if you're looking in the direction of a particular standard basis vector. But per the observation on the previous page, any unit vector could be a standard basis. Just set up your axes, right? And frankly, we shouldn't be thinking about things in terms of coordinates and variables anyway, because again, coordinates and variables are downstream from choosing your axes, which is arbitrary and made up. So the position I'm going to take here, and I think this is a really nice position, is that forget about what the vector is that defines which direction you're pointing. These four things relate for any unit vector, because any unit vector could have been a standard basis vector. Does that make sense to everybody? Everybody willing to believe that? Pick whatever unit vector you like. These four things are all going to be the same, because after all, that one unit vector, choose the right coordinates, is a standard basis vector. All right, so the idea of a directional derivative is to just kind of formalize this observation that coordinates are kind of silly, they're arbitrary, they have their purpose and convenient in certain ways, right? But they're certainly not intrinsically fundamentally meaningful. It's an arbitrary choice. So we're going to say, look, pick any unit vector, whatever, any unit vector at all. And the things that we described on the top half of this page, namely that expression, this dot product, slope of the graph, multiplicative factor, the various different ways that you can think about, well, what we started thinking about in relation to partials. For whatever unit vector you've got, you can talk about these four things, and they're still all going to be the same, because there are, with respect to some set of axes, these are all the partial derivative. Okay, so these are all equal to each other. That makes this thing that these are all equal to an intrinsically natural thing. It's worthy of a name and a notation, and this is what we call the directional derivative. Directional derivative of a function f in the direction of a vector, a unit vector v. And we use this notation, d sub v f of a, to represent that. So this is what a directional derivative is. I think that, again, the best way to think about directional derivatives is it's a rip-off of the idea of partial derivatives. Just, in some direction of some unit vector that doesn't happen to be a standard basis vector in the way you arbitrarily set things up. Okay. All right, so let me pause on that for a quick sec. Anybody have any questions about that? Okay. All right, so one other observation I'll make, and because of the way this is written down, we have an opportunity to make another interpretation. This is really more of a notation than an interpretation, I guess. But if you think about, what is it that you would multiply by ds dt or ds to get df dt or df? Right? What should we call the thing that we multiply by input change to get output change, given that we're going to write those input and output changes like so? And I think both of these equations make a reasonable case for the same choice, and that is this factor that I multiply to turn green into blue. df ds really makes a lot of sense. Right? And so this is a pretty standard notation. It's very convenient, especially in situations like this. And by the way, I know I've been discouraging y'all from the idea of thinking of differentials as something you can cancel. Certainly when you're doing the chain rule, it's absolute garbage, nonsense. You totally cannot do it there. In this case, questions as to whether you should, but you'll get the right answer. So this is a situation where it's kind of okay. It's not good as an argument, but it's good to justify a notation. It's good as a memory tool. That's all perfectly reasonable. Okay. So heads up, be aware. Sometimes we will refer to directional derivatives as DFDS. And this is a nice way to think, by the way. It gives the interpretation that we're talking about how fast the function's changing, because you see we're writing it as a derivative. But in particular, we're saying how much does the function change per unit distance that I move in the domain, right? Not, to be clear, not how fast is the function changing per unit time as I move in some arbitrary direction with some arbitrary velocity, right? That'd be a big difference, right? So, for example, give me 2 seconds. So if I'm on a hill and someone says, how fast is the altitude increasing? I would say, yeah, not that fast. I walk slow on a hill. Ooh, uphill? No, I'm going to take a nice slow pace. The altitude's not increasing very fast at all. And then, somebody who's younger and better shape than I am would say, oh, the altitude's changing real fast. Look at me run, right? And then they run right up the hill. Altitude's changing really fast, right? So how fast the function's changing with respect to time depends on how fast you're moving. Natural, right? DFDS does not. DFDS says, look, I don't really care about how fast you're moving. I don't even care if you're there. You don't even have to be there. Per unit distance, how much does the function increase? Walk that distance quickly or slowly, whatever, but per unit distance, you move a little distance, the function changes by a certain amount. That's what we want to know. Okay, yeah, sorry, question.
So previously we did like df dt was the output velocity. So is it the output, like does it give us the direction? Like what would be the main difference between both?
But between df/dt and dfds?
Yeah.
So dfds is intrinsic to the function and doesn't depend on knowing how fast you're moving through the domain, right? df/dt depends very much on how fast you're moving through the domain. Again, if I run up the hill versus if I just kind of slowly, walk up the hill, df/dt is going to be very different. But dfds just says how steep is the hill. And it's the same steepness whether I run or walk.
Okay.
Does that help?
So df here represents like the output of the steepness.
F represents altitude.
Okay.
Right. So you see, I've got a picture here. So the value. This is a graph right here. We're looking at z being the value of the function. So F represents altitude. df, you might say, represents an incremental increase in altitude. ds represents a distance that I'm moving along the domain.
Okay, thank you.
Sure. Okay, so let's see an example. We've got some function here, and the question says compute the slope of the graph. Blah, 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 details. All right, well, the question says slope of the graph. I have interpretations. I have interpretations that say slope of the graph is one of my primary interpretations of directional derivative. The question's asking me for slope of the graph. Cool, I'm going to compute the directional derivative, which, by the way, I'm going to do by way of that formula right there. So, okay, here we go. Slope of the graph, directional derivative, and I'm going to compute with that formula right there. Everybody on board? Now, there's one little sticky wicket on this. You got to be careful about this sort of thing. The vector that's given to me is 3, 4, but it does say in the direction of the vector, and furthermore, this concept here, this directional derivative thing, you remember, only makes sense if u is a unit vector, right? So back up to here, we need for our vector down here to be a unit vector. It's got to be a unit vector representing moving in some sense with a unit speed. Okay, so we were not given a unit vector. So the vector that I plug in here, the vector that I'm going to do the dot product with, it can't be this non-unit vector. No fair. I've got to take my non-unit vector that was given, and I've got to find what is the unit vector that points in that same direction. Right? I'm, after all, interested in the direction that this vector points. And so I'm going to take this vector, and divide it by its own magnitude. Now I've got a unit vector. And so it's okay to talk about the directional derivative in the direction of the vector u, because u is a unit vector, and so we dot product with this u. Yeah. Oh, I'm sorry. I thought that was it. Okay. Yeah. Okay. Yeah. Cool. Okay. So do be careful about that, and you'll see that denominator of 5. You got to carry that all the way down, of course. Bunch of arithmetic ensues. You got to compute the gradient vector, blah, blah, blah. A bunch of little details in here. That's the big strokes of the idea. Okay. Now, one other little terminological thing I want to make sure you all are clear about. This is, again, subtle, but it's important. Let's see here. Let me draw a quick picture. We are at the point 3, 1. I'm going to put a spot here. There's 3, 1. That's where I am. And now it says in the direction of the vector 3, 4. Now here's what a lot of students will do wrong. A lot of students will look at this phrase in the direction of and think, oh, that means toward. And that's wrong. Because it says here, V is a vector. Vectors don't have a location. When you walk towards something, you're walking toward a location. Right? So it would be completely wrong to say, okay, well, let me draw 3, 4. 3, 4 is about right there. And that's 3, 4. And then in the direction of, interpreting that as toward would mean like that. This is a complete misinterpretation of the phrasing. But you can see how it's tempting, right? How a lot of students might misunderstand, misinterpret what's being said there. So again, you got to be careful, make sure to interpret correctly. V is a vector, not a point. There's no point of interest right there. We're interested in the vector 3, 4. Let me get rid of that. The vector 3, 4 is like this. That's the vector. The direction of that vector is the unit vector pointing in that direction. Like so. That's the direction. And at A, moving in that direction, is like that. So it's not that way, it's that way. So make sure to be careful about that distinction. Make sure to understand that there is, again, we have this convenient kind of canonical relationship between vectors and points, and that's very nice, and you can blur the distinction if you are very careful to always interpret, as you should, from the usage, which one is actually being talked about. And so, again, nice little landmine to be aware of there. Okay, all right, next example. Very, very similar. We've got some function. We're at some point. And the difference here is that this time the question has not asked for the slope of the graph. Here, the question has asked for dt ds. Now, going back again up to here, derivative with respect to distance is one of our new interpretations of directional derivative. df ds is directional derivative. So again, instantaneous, you ask me for the rate of change with respect to distance. Cool, directional derivative. And again, I'm going to compute it with that handy formula right there. So same beginning of the problem. I've been asked for something that is, in fact, exactly the directional derivative. And I compute with dot product with the gradient. And again, watch out. You got to make sure you remember to turn this into a unit vector, right? This is not given as a unit vector. You've got to normalize, right? Divide by its own magnitude. And yeah, you got to compute the gradient and plug in the point in question, etc. A bunch of details. Make sure you all read through all those details, but that's same basic idea. Is that cool? Yep.
So whenever they ask the directional derivative, we basically are calculating the slope.
Say one more time.
Whenever they ask for the directional derivative, are we basically just calculating the slope?
Slope is one of the interpretations, but that's you got to keep in mind that's limited to if you're looking at the graph, right? So the word you say slope by itself, now I'm scared. I don't know what you're talking about, right? Slope of the graph, but think of that. I would encourage you to think of that as one of several interpretations. It's not really fundamentally the thing, right? I know it's the point of view on derivatives that gets pushed ultra hard in the Calc 1 classes, right? And I would suggest that's something it'd be good to try to pull yourself away from clinging to that single interpretation when in fact it's one of many. And again, you go back to here. Yeah, it's one of many. It's yes, it's slope of the graph, but it's also a multiplicative factor, and it's also rate of change with respect to distance. Yeah. Okay. By the way, I'll further point out on this question here, we're not looking at the graph. We couldn't possibly look at the graph. The graph would be a picture in 4 dimensions. So talking about the slope of the graph here actually would be adding a lot of ugly questions that we really don't want to do. Yeah.
Because the function is a 3 to 1.
Yeah.
Why is it like a 3 by 1 vector instead of matrix, the gradient?
So you do keep in mind that those are commas, not spaces. Comma means new line.
Yeah, but that's
right. So this is a column vector. Gradients. All vectors really are column vectors. All geometric vectors written as matrices are column vectors. As this is. Did I answer your question?
Well, I kind of mean like normally how if we have like a function which is like 3 input variables,
yep,
like 2 output.
Yes.
The like matrix of that would be 2 by 3, no? Or did I get that backwards?
So if 3 input, 1 output,
yeah.
Inputs correspond to columns, means that you would have 3 columns. There's 1 output, outputs correspond to rows, that means you'd have 1 row. So the derivative matrix would be a single row.
Yeah.
This is not the derivative matrix. Oh, this is the gradient vector. Yeah. So I think, you were conflating. Yeah. Okay, yeah.
Wait, how did this become something that lives in the 4th?
Well, the graph. Yeah. So there's nothing about 4 dimensions anywhere in this question. But somebody said the word graph, and I was like, wait, graph? The question didn't say graph. And in fact, we really shouldn't say graph, because if you want to talk about the graph of this function, it's a 4-dimensional picture. So, because there's 3 input variables, and there's 1 output variable, which means we have a total of 4.
Oh, I see.
Yeah. So I strongly advise we not bring up the graph of this function. It's I can't even begin to visualize such a thing. The question doesn't have anything to do with graphs.
So would you think, like, as you change, like, if this was like a surface, if you change like your distance, this shows how much the temperature is changing?
Yeah, that's right. So here we're computing the directional derivative because it answers for us what we were asked. How much does the function change per unit distance traveled in whatever direction we're going? Yep.
Is that a better, like?
In this case, this is the I don't want to say better. I mean, every situation is different. This is a reasonable way to interpret directional derivative here. Yeah. But I think, thinking about slope of the graph would be a huge mistake on this. It's 4-dimensional. I don't know what's going on there. Yeah. Okay. I have an awkward cultural point that I have to bring up. It's just a difficult situation. This is not a right versus wrong thing. This is a sometimes yes, sometimes no kind of thing. Let me start off being clear about what we're going to do in this course. In this course, this is the definition of directional derivative. Let me be perfectly clear, and I'm going to highlight here. So directional derivative, noted by that, is defined as this, computed by that, interpreted as a slope or a multiplicative factor. with the understanding that this is only when V is a unit vector. And here's the thing. Some people like to remove the requirement that it be a unit vector. And that changes things quite a bit. If you take away the idea that this is a unit vector, well, it's no longer the slope of a graph. It just doesn't work. It is no longer the multiplicative factor as described there. So you got to give that up. And then, by the way, furthermore, this whole business about it being DFDS. I mean, let me get back to, whoopsie. So we interpret it as DFDS. Yeah, that goes out the window also. If you remove this requirement of it being a unit vector, some things still work, but these interpretations do not. They disappear. Now, why would anyone want to do such a thing? Look at that. We just lost some nice interpretations. How is this a good choice if our interpretations disappear? And the answer is this applies much more broadly. This applies for any vector. And it is pretty cool to recognize that if you are interested in, and let's look at exactly what this says. I need to make a color choice here. I get, okay. Oh, gosh, I don't know. Orange. For any vector, you can reasonably ask, hey, when you're at some point A and moving with that velocity, you reasonably might want to know how fast the function's changing. That's a very reasonable question. Very natural question. Very handy to know that you can compute it with this convenient formula, gradient.v. Any vector, right? You can compute df dt with this formula for any vector. That's a useful concept, and it applies way more broadly than if we had this very narrow restriction that we only even entertain unit vectors. Right? That narrows our interpretations quite a bit. It's a pro-con thing. Different people have different points of view. Now, I again want to be perfectly clear. Our book has chosen to require that these be unit vectors, in which case we get all these nice interpretations, and that's lovely. Math219 is going to stick with the book. I feel like we kind of have to. But for whatever it's worth, for your consideration outside of Math219, when I'm just doing math business and my own business, I'm one of these guys. I don't like to restrict myself to unit vectors. And there's plenty of us out there, right? It's a pro-con thing, right? But I use the term directional derivative broadly outside of this course. So for your consideration. The other point I wanted to make, and again I call this a cultural point because different people are going to see this in different ways, and it's a pro-con kind of deal. You should be aware that there are others out there. It's not just me, right? Who will use the term directional derivative. Sometimes they mean unit vector, sometimes they don't. And unless you know who you're talking to and which camp they are in, right? Or what kind of a mood they're in at that particular moment, right? Maybe they use one sometimes and the other times, right? That's also reasonable. There is a significant potential for confusion. So heads up, right? Outside of Math219, make sure you know who you're talking to, and make sure you don't create a misunderstanding. Okay. All right. Okay. So here's a reasonable question to want to talk about, and this is what I'm going to call a reasonable question that will lead to a really interesting answer. So we've got some multivariable function. Cool. Differentiable, so life is good. We're at some point A in the domain, and from that point A, we're going to consider all possible directions. And again, keep in mind it's convenient to represent directions with unit vectors. So there's a bazillion different unit vectors describing directions that we can move from that point. And here's the question I want to ask. Suppose that I'm interested in the directional derivative. And keeping in mind, when I say directional derivative, I mean directional derivative in the direction, whichever of these many directions I end up choosing. Right? Which of these many directions will make this directional derivative as big as possible? I think this is a reasonable question, right? This is a very natural question. I mean, look, sometimes I'm at a place and sometimes I want something to increase as fast as possible, so I want to make my directional derivative as big as possible. Right? Maybe I'm cold and this is temperature and I want to make the temperature increase as fast as possible. Perfectly reasonable. Right? Maybe this isn't physical location. Maybe this is the various parameters that go into the design of some engine. I don't know. Right? And maybe the output function is efficiency. And you want to ask the question, in what ways should I be tweaking these various parameters to make my efficiency increase as quick as possible? Right? Very natural, very reasonable question. Okay. All right, so one of these will be the right answer. We don't know which one yet. Let's just say it's this one. I don't know. Whichever one it is that maximizes that directional derivative. We have a couple of different names that we could reasonably call it, and what's the motivation for these different names? Well, if you want your function to be increasing as fast as possible, I think direction of fastest increase makes loads of sense. It's a very natural choice of term. If you should happen to be looking at a graph, now keep in mind, if you're looking at a graph, the output value sort of attaches to the domain. Typically, we draw the output as being up, right? And making that output increase as fast as possible means you'd be going in whatever direction's making your graph go up as fast as possible. Direction of steepest descent would make sense in that, from that point of view. So the reason I mention these two terms is that both of these are out there, and I want you all to be on the lookout for both of them. And to my slight frustration, the one that's the most common is this one right here, direction of steepest descent. And it just kind of bugs me a little bit, not a lot. I won't lose sleep over this. But, I mean, it only makes sense if you're looking at a graph. It only makes sense if the function in question is literally up. There's lots of things that we look at that we don't draw graphs of, can't draw graphs of. Have no particular need, even if we could, to represent as being up, and to draw graphs of. So I personally actually like this term quite a bit better. This makes sense in any context, whether you're looking at a graph, not looking at a graph, whatever, I don't care. Direction of fastest increase, because that's the direction you go to make your function increase as fast as possible, right? It just makes loads of sense. So I'm going to probably say direction of fastest increase most of the time, right? But y'all should be aware, again, cultural point, outside of Math219, you're going to see direction of steepest descent probably more often. And again, it's kind of narrow, and it doesn't make sense in other contexts, but that's the common term. Okay. All right. Okay, so that's the question. Let's figure out how to answer this question. Let's see here. I'll just do it like this. How are we going to find that direction? Well, here's what we're trying to maximize. I want to make that as big as possible. We compute that with a dot product with the gradient. We want to make that as big as possible. Dot products are computed with this formula. That's what we want to make as big as possible. Oh, wait a minute. Our vectors V are all unit vectors, so that means this factor right here is 1, so let's get rid of that. So this is what we want to make as big as possible. Oh, and one other thing. Don't forget, I am at this point, A, and I'm not moving. I'm here at this point A, I'm thinking about moving. I'm thinking about all the different directions. Maybe I'll go that way. Maybe I'll go this way. I'm contemplating moving, but I'm not actually moving yet. I'm trying to decide which direction to move. So A is constant, which means the gradient is constant. So this is a great big constant. Okay, so you boil it all down, and what is it that I really need to do here? I need to make cosine theta as big as possible, and that's an easy question, right? We maximize cosine theta by making theta equal to 0. So back to the picture, keep in mind all of this, the point of all of this was that the gradient and the v vector, right? I'm looking at that dot product. The dot product is going to depend on this angle. That's the angle between those two vectors, and we just agreed that you maximize that when theta is equal to 0. So my picture here of what this v vector ought to be doing, I need to orient my picture so that that angle is 0. And so what that means is I drew my picture wrong. It just means I need to, my unit vector should be like that, so that that angle between those is 0, yeah.
Wait, why is it maximized when theta is equal to 0?
That's just trig, right? Cosine theta. Just think about the biggest cosine theta can ever get is 1.
Oh, okay.
When is cosine theta 1? Yeah, that's, just trig, yeah. Okay. So, all right. So, all together then, nice simple answer. What's the direction of fastest increase? It's the direction that the gradient points, which of course is gradient divided by magnitude and gradient. Yeah?
Can you explain why the magnitude of the gradient is a constant again?
Oh, well, the gradient is a constant because, the gradient is a function of where you evaluate it, and the whole point to this is that I'm not moving. Right, I'm at this point A, and I'm just sitting there. I'm just contemplating different directions, but I'm not actually moving yet. A is, in fact, still a constant. Does that make sense? Yeah. Okay. Okay, let's ask the natural next question. So we've figured out what is the direction of fastest increase. Oh, okay. Well, in that direction of fastest increase, how fast is it increasing? Pretty natural question, again. Right? And again, nice easy answer. Directional derivatives are dot products with the gradient. Our vector v here, we just agreed is that. And then you look at this self dot product of the gradient, of course, is magnitude squared. And therefore then the directional derivative is just magnitude of the gradient. Nice little easy little calculation there. And so this gives a really nice, you might call this a summary. I like to call this a geometric characterization of the gradient vector. And I want to remind you before we get into this, what do we know about the gradient vector? So far, before today's class, we knew two things about the gradient vector. We knew it was a notational convenience, right? We were writing down linear approximations, and I hate having to write all these terms. Let's call this thing a gradient, and then we can just use dot product, and it makes our formulas more compact. Right? So the gradient was a notational convenience. We also knew that in some situations, the gradient behaves like a derivative. It's the thing that you multiply by input changes to get output changes in certain situations. And I would call both of those algebraic takes, right? Algebraic perspectives on the gradient. So what we have now is a geometric point of view on the gradient. It's a vector. It's got a direction and a magnitude. The direction is natural. The direction is whatever direction the function is increasing the fastest. That makes the direction a natural thing. The magnitude is also a natural thing because the magnitude is and take your preferred natural interpretation. It's rate of change of the function with respect to distance, or its slope if you're looking at the graph. Whichever take you like. But the magnitude, again, natural, geometrically natural. So what's nice about this is, again, even though we came into this thinking of the gradient as being a fundamentally algebraic thing, now we can say, you know what, it's really geometrically very much a natural thing as well. Yeah.
Can you think of the directional derivative as like the component between
The what now?
the component between the gradient and the vector times the length of the vector?
I mean, it's a dot. Well, let's see. Maybe say it one more time. I'm sorry.
Can you think of the directional derivative as the component of the?
Oh, I hear you.
With the gradient times the length of the vector.
I mean, I would call that computationally valid. I don't know if I think it's a helpful way to think about it. But yeah, I mean, directional derivative is a dot product. Dot products with unit vectors are components. So yeah, you can make that work. It's algebraically true. I'm not sure if I see how helpful it is. But that's, everybody's going to have different points of view of, you know, what makes kind of the most sense in their mind. Yeah, totally. Okay, good question. Yeah. Okay, let's see an example. By the way, these are really convenient examples. These are the kind of questions, by the way, that you got to be fingers crossed. I hope this comes up on an exam because they're super mechanical. If the question says, what's the direction of fastest increase? However that might be phrased, right? The English language has a lot of flexibility in it here. Here I said it differently. Which direction is uphill? That's what's the direction of steepest descent? It's the same thing, just different words, right? Communicating the same idea. And how steep is it? Okay, well, but that's basically just saying what's the directional derivative in that direction? Different language, right? So this is asking us pretty much to just compute the gradient. So broad strokes, we'll get to the detail in a second. But yeah, so I compute the gradient. We're interested in what's happening at this point, 1, 3, so I plug that in. And the specific the specific gradient that I'm interested in is that one. That's the gradient at the relevant point. And there you go. You can see what direction that points. That's the direction of fastest increase. And you can see what its magnitude is. That's how steep it is in that direction. And just to put that onto the picture, here's that point we're at, 1, 3. This vector, -2, is about like that, I suppose. And by the way, do keep in mind that when we draw maps, it's arbitrary, but nevertheless fairly standard, that north points, up on the page, which is also how we typically draw the y-axis. The y-axis is typically up on the page. Not that you have to, it's totally arbitrary, right? But typically. So consistent with that, I'm going to say this direction here is north. And geometric appeal, if that's north, then that vector is pointing what you might call southwest. Everybody buy it? All right. Okay. Now, one little annoyance we've got to talk about. We do want to distinguish between this point, 1, 3, and where I actually am, right, on this picture, right? We've got a hill, and golly, look at that. That point's buried like way deep underneath the hill. That's not me. I hope it's not me, right? I'm actually way up here standing on the side of the hill. Okay, so I did indicate that here by say the point sitting above 1, 3. The thing is, in practice, that gets tedious. In practice, we normally kind of sweep that point under the rug. If I say, hey, I'm on the hill at 1, 3, yeah, you're supposed to know I'm on the hill, not under the hill, right? So most of the time, people will just say, I'm at 1, 3. And of course, it's understood that you're actually in 3 space. not into space, right? So another way to say this, we describe our location in 3 space very often by just giving the map coordinates. Longitude and latitude perhaps are maybe one way to think about these, right? And then it's understood that, of course, you're on the surface of the Earth. Had you not been on the surface of the Earth, that would have been something to clarify explicitly, right? Okay. So heads up, the distinction between these 2 points. This is very often just kind of understood. That means, translated differently, it's your job, right, to understand that a potentially sloppy description like this actually is a reference to that, and you just got to make the appropriate interpretation. I saw a hand somewhere, and then I was on a roll. So did somebody have a hand up? No? Okay. All right. Okay, moving along. Where's my thing? Here it is. Okay, so let's talk about level sets. I'm going to make an innocent observation. It's going to turn out to have a really powerful punchline. And here we go. We'll start by saying we're looking at a level set of some nice function. My picture here assumes that we have 3 variables. So f equals c is an equation of 3 variables, gives us a surface. Again, I emphasize this is a level set. F is constant everywhere on there. And now here's my innocent observation. Unremarkable yawn of an observation. As long as you stay on this surface, f doesn't change. I'm going to say that ever so slightly differently. As long as you stay on this surface, the rate of change is 0. Right? If it's not changing, then the rate that it's changing is 0 because it's not changing. Right? I think this is, again, pretty clear. So here's a reasonable scenario. So let's suppose I'm moving along the following curve. I need to be able to see better to draw. I suppose I'm moving along this curve like that. Now I am entirely sticking in this surface as I move along that curve. F is not changing as I move along that curve. The rate of change of f is 0 as I move along that curve. So, in fact, just to say that a little bit differently, when I am at this point and moving with the velocity of that curve, when I'm at that point moving with that velocity, the function's rate of change is 0. And what can I say about this velocity vector? Well, it's a tangent vector to the curve, and therefore it's a tangent vector to the surface. And I make the observation, you can do that for any one of these tangent vectors. Every tangent vector to the surface is a velocity vector for some curve. The function's not changing. Right? So for any tangent vector then, let me get rid of all the rest of this. For any tangent vector to our surface, the rate of change of the function is 0. And now I'm going to remind you, but the rate of change of the function is the directional derivative. Directional derivatives are computed with that dot product with the gradient. That means that that dot product with the gradient is 0. And wait a second, when a dot product is equal to 0, that means that we have orthogonal. So this is a pretty nice conclusion. I mean, it comes out of, again, making this silly observation that if f is a constant, then it's not changing. Right? This, of course, observation, we get this nice conclusion that gradients are always orthogonal to tangent vectors. And said differently then, gradients, being as they are orthogonal to all possible tangent vectors, I claim that gradients also have to be orthogonal to the surface. So this this perpendicularity that I've drawn in the picture there, gradients are always perpendicular to level sets. One important little distinction, it's an easy mistake to sort of ignore. when I say gradients are perpendicular level sets, gradients of the function whose level set you're looking at, right? The function whose gradient you're talking about, the function whose level set you're talking about, that's got to be the same function, right? But that being the case, yeah, gradients are always perpendicular to level sets. And this is a good place to end it for today, and we will pick up here on... No, we won't. Friday we have a test. Don't forget, test on Friday. See y'all then. We'll pick up here on Monday.